Okay, so now let me give you what the desired performance is for the closed loop system. So desired closed loop performance specs. Okay, so I'm going to ask for a certain maximum level of overshoot, and I want the peak time to be below a certain value. Okay, so I want it to be fast, and I don't want the step response to oscillate. I really want the stage to move to position and stop there. Okay, so the two specs I'm going to give you are that I want the percent overshoot to be less than or equal to 20%, and I want the peak time, TP, which is pi over omega d, the damped natural frequency, is going to be less than or equal to 1 second. Okay, so these are the two specs that I have. And what we're going to do is we're going to check first if the proportional controller will work. We'll first check a proportional controller, and then we'll try a PD controller. That's going to be my approach. Okay. So let's look at the two constraints, 1 and 2, in terms of closed loop pole positions. Okay. So to have percent overshoot less than or equal to 20%, well, that's going to be a specification on the damping ratio. Okay, so I can go back to the lecture where I related zeta to percent overshoot, and you'll see that here's the formula. It's the natural log of the overshoot divided by 100, because I've got to convert it back from a percent to a decimal. And then I take on the bottom, I have square root of pi squared plus log squared of percent overshoot over 100 again. Okay, and so it turns out that if I plug in the numbers, gives me 0.5. So 20% overshoot, when I plug it into this formula, I get 0.5. So the damping ratio must be greater than or equal to 0.5. Okay, that's the first spec that I'm going to have on the pole locations. The second specification for the peak time, TP is pi over omega d. So I can write that omega d is equal to pi over TP. And since we have TP is less than or equal to 1 second, I find that omega d must be greater than or equal to pi radians per second. Okay, the damped natural frequency has to be greater than or equal to pi radians per second. Okay, so now what I'm going to do is I'm going to plot those two constraints. This is the second constraint. Draw a little red box around it. Okay, these are the two constraints I have. So now I can plot these in the S-plane, and this will tell me where the poles can be in order to meet the specs. So here's my complex plane. Okay, and I'll draw a line for the peak time. Okay, so it's like this, here, and here. Okay, and remember that, is that erase everything? Let's see. Okay, so this intersection is j times omega d, so we've got to have that be equal to pi. Okay, pi times j. So the poles are going to have to be above this line or below this line, right? They're going to be complex conjugate pairs. And then the damping ratio specification is a line that looks like this. Okay, and how do I know where that line is? Well, I know that the angle here, theta, is equal to the arcsine of zeta, okay? And zeta greater than or equal to 0.5. If I plug that into the formula, I find that theta has to be greater than or equal to 30 degrees. Okay, so this line has got to be, I could draw this line here at 30 degrees, okay? So basically any pole that, like, I could have a greater angle. Like, so if I draw, like if I have a pole that's, I'll just sketch one here. If the closed loop pole is here, if I draw the line to the origin, well, it's at an angle that's greater than 30 degrees. So that's what this requirement means. The angle of, if I draw a vector from the closed loop pole location to the origin, that angle has to be greater than 30 degrees. Okay, and so clearly it is for any pole that falls below this green line. So the allowable region for the poles is in here, okay, and in here, right? Remember, they're complex conjugate pairs. So these are the allowable pole locations that I shaded in yellow, okay? Now what I'm going to do is I'm going to start by plotting the uncompensated root locus, meaning I'm going to use just a proportional controller, and I'll see where the root locus lies. Okay? Okay, and so I used my knowledge of geometry to calculate the intersection of these 2 points. That actually is going to turn out to be important. And so that intersection happens to be at minus 1.8 plus pi times j. Okay, that's what this point is here. So this line here, sort of where these guys are at, it's at minus 1.8. Okay, and pi j, obviously that's from the peak time specification. Okay, I calculated that because I drew this 30-degree line and I found where it intersected that dashed blue line. Okay, so now what I'm going to do is I'm going to plot the root locus just for the plant by itself, and I'm going to clear off a little bit of stuff here just so it's a little bit more clean. Okay. Okay, get rid of that guy. All right. So let's go ahead and write the root locus for the plant itself. So GP is equal to 1 over S times S plus 2. And so basically what we're doing here is we're saying GC is equal to K, a proportional controller, and we'll plot the root locus. Okay, so I start with the 2 open loop poles, one here and one here at minus 2. And that's at x equals 0. Okay, and so where does the root locus lie? I'm going to draw it in red. Well, it lies on the real axis in between those 2 poles. And what happens is that for a second order system like this, they meet in the middle and they will break up and down like this. Okay, so they go like this. Okay, and where they intersect is at minus 1 here. Okay, and remember that this point here I calculated is minus 1.8 plus j times pi. Okay, and so clearly if I look at the root locus for the plant by itself, just with a proportional controller, there's no gain. The root locus never crosses into the good region because it's always to the right of this this point here. Okay, so I can never, I will never be able to have the, I will never be able to place my poles where I want them to be. And so one way we can think about it is if I meet the peak time specification, I'm going to have too little damping. So let's actually go ahead and calculate that. So the closed loop poles have omega d equal to pi, right? So then this will make the TP spec TP of 1 second. When they are here, right? So they would be at this point here and this point here. And we can calculate the damping ratio there, okay? So if I look back to the previous slide, the formula I used is that this angle theta is the arc sine of the damping ratio. And so similarly, I could calculate then if I know this point here, right? So let's see, what I know is that I'm talking about this length here is 1, and this length here is pi, and this is the angle that I want to calculate, theta, okay? It turns out that zeta is equal to 1 over square root of omega d squared plus sigma squared. This is omega d. This is sigma. And so when I plug in those numbers, I get 0.3. The damping ratio is 0.3. And clearly 0.3 is less than, not less than or equal to, but less than the zeta that I required, which was at least 0.5. Okay? So I can achieve the peak time specification, but I don't have enough damping ratio. I need to add some damping to meet the percent overshoot spec. Need, doesn't look like need. Need to increase the damping to meet. Okay? And so whenever you know that you need to add damping, you have too much overshoot, then that's a good time to add a derivative controller. Okay? So let's look at the transfer function for a derivative controller. PD controller transfer function. Okay? So it's GC of S is equal to KP plus S times KD, which we can rewrite as K times 1 plus S over Z, okay, where K is equal to the proportional control gain. Okay, so that's the sort of the gain of the controller, and the 0 of the controller is equal to KP divided by KD. Okay, so I like to use it in this form here because I'm basically going to place a 0 somewhere, and then I use K, right? I design K, the gain, using the root locus method, okay? So I just have to choose where the 0 goes, and then I use the root locus to pick K. And so later on, if we had to implement it in a system where we actually have like a derivative term and a proportional term, we could use these equations to convert my 0 and my gain into the proportional and derivative control gains, okay? So how are we going to do this? Well, the idea is that now we're going to have a root locus plot. The closed loop characteristic equation is 1 plus GP GC equals 0. And so we could write it as 1 plus K times 1 plus S over Z. And on the bottom we have S times S plus 2, right? Those come from the plant, equals 0. And so now what we've got is basically, it's the root locus form with the loop transfer function f of s is equal to 1 plus S over Z over S times S plus 2, okay? So it's basically the plant, but I've added an additional 0. And so I can place that 0 where I want to make the desired point, the desired closed loop pole position, be on the root locus. So if I go back, let's actually go all the way back to this guy here. So in particular, right, what I want to do is I want to take this point here and I want to bend the root locus so that this point, the point at minus 1.8 plus j pi, is on the root locus, okay? And then I'll have met the specifications, okay? And usually, right, so I could push them further into the left half plane, right? But the rule of thumb basically is that it's always nice to design, we kind of use sort of the minimum effort that we can to meet the specs. So we want to meet the specs, we don't want to totally blow them away, because usually there's some cost for that, right? We're going to need some very large controller gains, we're going to need like super actuators and stuff. So we're going to assume that whoever specified these specifications really meant that we should just try for the absolute minimum, okay? So let's make that assumption. Okay, and so the idea, let me sketch the beginning of the root locus here. Okay, so I'm going to put the poles from the plant on here at s equals 0.